Hey guys, welcome back to the channel. Today we'll be solving LeetCode 70, climbing stairs. So we're climbing a staircase and it takes n steps to reach the top. Each time we can either climb one step or we can climb two steps. And we have to figure out in how many distinct ways can we climb to the top. So this is a dynamic programming question, and there's going to be four different ways to solve this. And I'm going to show you all four different ways with different complexities. So the most efficient one is going to have linear time complexity with constant extra space. And there's also more efficient ones, but they do have linear space complexity, and those work too, but I'm going to show you all of them. So let's get into the explanation. Okay, let's start off with the backtracking solution. So initially, we start off at 0 steps, and we can either choose to take one step or two steps. So we can take one step here and two steps here. And we can do the same here. We can either take one step or two steps. And the maximum number in the example they gave was 3, so let's use that. And we have reached the maximum number of steps, so this is going to terminate. And then here we can take one more step, and then here we can take more, but this is not gonna work. The base case is gonna say this is too far, and it's just gonna return 0, so we're not gonna add that into our tree. And then we can take one step here, and that would return 3. And then we can take two steps here, 4, but that's going to be too far, so we're not going to add that to our tree. And this is pretty much it, and this should also be 3. And just by looking at this, you can tell the time complexity of this is going to be 2 to the n, because we're making 2 recursive calls in every recursive call. So it's going to multiply by 2. And this is pretty inefficient. So there's actually an optimization that we can make, and this optimization is called memoization. And if you look, you can see redundant trees that are getting reused. So in this case, we can see that this tree shows up twice. It shows up here and over here. So why would we calculate what the output of 2 is going to be if we already calculated it once? And since backtracking, the solution we're using is similar, it's like a DFS solution. We're going to go to the leftmost trees, and this right here is going to be calculated already. And when we get to here, why would we calculate this again if we already calculated here? What we can do is we can store the result of this in a memo, or otherwise known as a hash map or dictionary, and to we can just map 2 to whatever we returned from the backtracking function, which is going to be 3. And anytime we encounter 2 again, instead of calculating the whole recursive tree, why don't we just check the memo first and take from the memo? So in this case, when we get to this recursive call from the DFS function, we're going to check, oh, there's already a 2 in the memo, so we're just going to return 3. And this is going to run in O of n time, because our tree is basically just going to be this. It's just going to be a really long vertical tree, and any branches off to the right side are not going to need to be called, because we're already going to have the value in the memo. And the space complexity is going to be O of n, because we're storing the stuff in the memo and we're making recursive calls. So we're going to have O of n memory and O of n time complexity. So now the question is, can we do better than linear space complexity? And the answer is yes, we can do better. We can actually achieve constant space complexity, and we're actually going to still start with linear space complexity, and we're going to work our way to constant. But we're actually going to code up an iterative solution, and we can do this by looking at the problem first. Notice how 0 depends on this subproblem and 1 depends on this subproblem. So they depend on each other. So what we're going to do, instead of starting from the top, we're going to start from the bottom and work our way to the top. And this is called bottom-up dynamic programming, or tabulation. And I'm going to show you how this works in a second. So I'm going to use 4 steps in this case so it's easier to understand for larger examples. So we're going to start at 4, the top step. And we're going to see how many ways can we reach the end. So the end is 4. There's only one way we can reach 4, and that's to reach 4. So we're basically already at 4 and there's only one way. This is going to be sort of like a default value. So there's only one way we can reach it. And then we're going to see how many ways can we reach 4 if we're at 3. So we can either go to 4 or we can go out of bounds. But out of bounds is a count and we need to get to 4. So there's only one way that we can reach 4. And then we're going to check how many ways can we reach 4 from 2. We can just go straight to 4, which is one way, or we can go straight to 3, and then 3 can go to 4. So how many different ways would that be? That would be 2. So if you're noticing by now, this over here, this step depended on these 2 steps. And it was actually a summation of these 2 steps. And then you're probably wondering, how many ways can we reach 4 from here? We can either jump to 3, or we can jump to 2. And if we jump to 2, then there is 2 more ways to reach 4. And if we jump to 3, there is 1 way to reach 4. So therefore, there is 3 different ways to reach 4 from here. So the answer for this question specifically is going to be 3. There is 3 ways to reach the top. And as you can see, we stored an array. So at the end, we have an array of all the values, and we're always going to return the first value. But notice, did we need an entire array to do this? No, we didn't. We actually only need the last 2 values because the new value depends on the last 2 values. So in reality, we can have constant memory with 2 variables where we store the current and previous one. And if you haven't noticed now, this does look a lot like the Fibonacci sequence, and that's because it is. This question is just a different form of the Fibonacci sequence. So in our best case, we're going to have linear time with constant extra space. So let's get into our code now. So let's start off with our backtracking solution. And this is going to be our least efficient solution. It's going to be the brute force. So we're going to start off by defining a backtracking function. And this is going to take a integer called steps, and that's going to count how many steps we have taken so far. And it's also going to return an integer that's going to be also the amount of steps we have taken so far. And if the number of steps we have taken ever exceeds the amount of total steps on the stairs, we're going to return 0. But if we reach the top, we're going to return 1. And that 1 represents one way to reach the top, and the 0 represents it. 0, it represents something that we can't reach the top. That's what it means. So we're going to return 0 because that doesn't count as a specific way to reach the top. So our 2 base cases are going to be, if steps equals n, we're going to return 1. But if the steps exceeds the number of total steps on the stairs, we're going to return 0. And then we're just going to do a backtracking function call where we're going to call to two separate ways we can take on our backtracking tree. We're going to take either one step, or we can just take two steps. And this is why the solution is going to be 2 to the n, O of 2 to the n, because we're making two recursive calls here. And at the end, we can just call our backtracking function, and it can start at n, or not n, sorry, 0. And basically, this is just going to keep going until we reach the end. It's going to return all the ways we can reach the top. Now, can we improve this function in any way? And the answer is yes. We can make this function run in linear or O of n time, and that's going to be using a memo. So what things do we need to change? So we're making a recursive call every single time, but we don't need to. If we can already see it in the memo, why would we make the recursive call? So before we make the recursive calls again, why don't we just check if this specific amount of steps is already in our memo? And if it is, let's return the value stored in the memo. And afterwards, if it isn't stored in the memo, what we're actually going to do is we're going to add it to our memo like this. And after that, we can just return the memo again. So if this evaluates to false, that means it wasn't in the memo. So we're going to add it to our memo and then return what we added to the memo. And this is pretty much the tab or the memoization solution, and it's going to run in ov n time with ov n space complexity. So let's now get into the iterative solutions. So let's just run this real quick and see if it works. Looks like we have a small bug. Oh, there's a colon there. Looks like it worked and it's pretty efficient. Now let's get into our iterative solutions. So to solve this problem using an iterative solution, we're going to start off by storing an array that's going to be the size of the amount of steps on the staircase plus 1. And we're basically just going to initialize the first two steps to 1, because in any case, they're always going to start at 1 and it doesn't change. And you will see this in the Fibonacci sequence as well. And then we're going to loop through this array. And since we already calculated the first two steps, we can actually start this at the third index. And we're going to loop till we get to the n plus 1 step. And at every step, the ith step is going to be the previous two steps. So it's going to be I minus 1 plus steps of I minus 2. And after that, we can just return the last step, which is going to hold our answer. So we can make an optimization to this. Notice we're always reading the last two values. So if we're only reading two values at a time, why would we store an entire array? What we can do is just store two variables that hold the previous and current values, and they're both initialized to 1. And we don't even need I in this case, so we can just set that to an underscore. And we're basically just our previous is going to become the current, and the current is going to become the previous plus the current, because the new value is actually going to be the new current, and it depends on the previous two values. So we can use Python's one-liner to swap two variables. And this is all we have to do for the for loop. And at the end, we're just going to return the current value, which is going to hold our answer. And this is all of the code we need. And since we're only storing two variables, this is of constant extra space, and it's going to be the most optimal solution. Thanks for watching, guys.